an enzyme that does something, or antibody or something. So that's more. So it depends on the question. And um, yeah.
Can I ask a question? Maybe it's not related to last week, but why do you assume that the differences between different people is due to noise and not due to other parameters, like eta and beta?
I see. Why do differences between people are not differences in eta and beta, but rather due to noise?
Yes.
Okay, so in mice, we can be sure that genetically identical mice,
Okay.
same conditions, die at different times, and they have this. So we can know that situation.
But maybe they still have different eta and beta.
How?
How do you call it? Epigenetics or other things. I don't know.
Yeah, it's true. They might have yet unknown effects, but you don't need them in order to explain this. And then you also see this in yeast cells, and you see them in worms, and so it becomes hard to believe that it's. And also remember that genetically identical twins, you try to understand the genetic component, and it's not very high. It's not, for sure, not everything, or environmental. But actually, we'll have a lecture about that, the genetics of aging. So we're interested in that question. Good. So and last time we solved it. So we got that the hazard risk of dying at age t and we got that h0 looks like this and alpha looks like this. So what does this mean? The faster your trucks are working, or the higher your threshold, suppose now you're at age 0. What's the chance for noise to kick you over the threshold? It's really, really low. The higher the threshold, it's exponentially low. The faster the trucks are working, very low. And noise, the higher the noise, the easier it is. Or if noise is 0, this is infinity, so it's 0. So this is like how the trucks set the risk of dying at age 0, you can call it, from age-related diseases or reasons. It's very, very low. And the slope here, this doubles over every 8 years, comes to be the rate that houses are built. That determines it. That's very important. The rate that houses are built determines how, it basically determines how long the organism is going to live. So in mice, it's about 60 times smaller than, 60 times faster than in humans. This is this slope. So and it's also in the lecture notes we solved it. So I'll just write, this is H0. It's like extrapolated risk of dying at age 0. It tells you about the trucks and the threshold and the noise. Because at age 0, there's still no houses. And then this rate of increase tells you something about the houses. The more houses you build, the faster the garbage accumulates, and then noise can push you over the threshold. And the more garbage you have, the easier it is to get pushed over the threshold, and that goes exponential because you have a linear rise, and that makes the number of random steps you need smaller and smaller. So it's like needed to throw less coins. In order to get heads, 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 here you need to throw 10 coins, here 9 coins, here 8 coins, and that becomes exponentially easier. Half times, half times, half. 9 times, half times, half times, half. 8 times, it's like a geometric series. So a linear process, coming closer and closer to the threshold, makes noise needs to work less hard. That's how linear increase in houses gives you an exponential risk of dying. By the way, if houses didn't go like eta t, but went like something t squared, like parabolic, instead of the Gompertz law, we would have alpha t squared here. But we don't. So inside the process of this model, the linear rise in houses is essential to get an exponential rise, not exponential t squared or something like that. So that's okay. So this is a review. So maybe now we'll do the pair and share. Just to, I'm sure there's questions on both sides, biology. So please turn to somebody next to you, ask a question, and then we'll collect questions just because it's a review. I want to see that it's sitting okay. So please turn to someone next to you. Don't leave anybody alone. יש לך פה מישהו? Yes, Glenn, you have someone 2 rows behind you. You don't leave him alone. So. Ask a question, like something maybe. You guys should move forward because you can't really. It's also I have to shout in order to reach you. So would you guys mind moving forward? So it's make it easier for me. Okay. So any questions you want to share? Any questions you want to share? I'm sure the questions you have, other people also have. Yeah. I did that last time. There was the bowl, and there was first passage time process, and U potential, and drops linearly. Yeah.
You mentioned a couple of times that this analytic solution results in decrease in the coefficient of variation, the ratio of the standard deviation
Of the mean to the of x.
Yeah, but I don't recall if we explained how this result ends up in reducing
Yeah.
the.
So your question is, I said that the standard deviation of x divided by the mean, is the coefficient variation in old people is smaller than in young people.
Yeah.
That comes from the model in simulations and analytical solution, but I didn't explain it.
Is there like an intuition from the?
No, that's one part where I can't explain it yet. Maybe you
Even
guys.
though like you have a noise term that rises with time,
Noise doesn't rise with time here.
it's like isn't it the square root of? You said.
Oh,
last week
yeah,
that-
yeah. What I said was when you simulate, you propagate this with time step delta t. This has to be propagated as time step square root of delta t. But noise here is constant in time.
Mhm.
Most processes that you simulate give coefficient variation that's constant. This is very weird. It drops with age, because I think the mean rises really, really quickly. The mean rises really quickly because the trucks get saturated. So you have houses and you have a maximal truck capacity, and close to that, the mean. starts rising very quickly, and standard deviation doesn't catch up. But I don't know how to explain it intuitively. But it's a fact that comes from simulations. What other questions? Yeah.
Why doesn't our body have like some kind of mechanism to increase the number of trucks at
Okay.
the scale at which they
Yeah, why not increase the number of trucks? So I think for most kinds of damage, there's a mechanism to increase the number of repair systems. Those kind of systems don't drive aging because trucks never get saturated unless they reach a capacity. If they reach a capacity, then you can't increase anymore. So the layers of the onion that we see are ones where either there's no trucks or the trucks get saturated. The body doesn't. Why doesn't it? We evolved to be young, and these trucks are for injury, viral infection, cancer. We're not evolved to be old. This situation where we're full of damage is not something in our design. So, and also, yeah, there's a limit to how much white blood cells you can have. Blood is already full of red blood cells. It gives you oxygen in the blood at the same concentration as oxygen in the air, which is incredible. Maybe there's also physical limitations. But if the trucks could follow, there would be no this. There would be just constant damage. There's many things like that, but they don't drive aging. So interesting. Okay. And of course, all of this stuff is in the lecture notes, which is on the website. And now I want to talk about diseases. So what I want to tell you about the aging-related diseases is really striking. So in diseases, there's something like hazard. There is the concept of incidence, which is you take, let's say, 100,000 people from the population who are without the disease, without a certain disease I'm interested in, and ask how many are diagnosed, let's say, at 100,000 people at age T. How will you diagnose this year? So between age T and T plus 1 or something like that. Right, it's important to me to say it's 100,000 healthy people. Let's say we're talking about cancer. They don't have cancer. They're all 64. How many will be diagnosed in the coming year with cancer? That's called incidence. Explain myself? Try to be very formal. Incidence. And incidence looks like this. So the four horsemen, right? So we have cancer, diabetes, neurodegeneration, and cardiovascular disease, but also cataract, osteoarthritis. I drew here with the same height. It's not just true. Some diseases are rare, some diseases are common, okay, but the shape is, they rise exponentially and then they drop. And when we did a survey of Clalit, so we have all Israel medical records from the last 20 years, 50 million life years of half the Israeli population. And you look for ICD-9 codes, which are disease codes. There's a systematic international disease code, ICD-9 codes of disease. Now it's up to 11, I think. You look at the diseases and you calculate the incidence. You find 1,000 diseases, ICD-9 codes, that change, let's say, more than 20-fold between age 20 and 70. And they all look like that. And the slopes are very similar, not identical, 3 to 8%. So there's got to be something here because these diseases are so different. Cataract is different from hypertension, which is different from cancer, which is different from osteoarthritis. By the way, this disease is so common, maybe a third of all people over 70, they have pain here, knee replacement or hip replacement. Hip replacement is a really good surgery, it works. Hip replacement is less. But why is it so important is because when it hurts you, you stop moving so much. When you stop moving so much, your metabolic syndrome grows. When your metabolic syndrome grows, your cognition goes down, and your risk of cancer grows. So it's like a cascade. So this is gerontology. It's multiple diseases. So the chances of getting more than one disease also rise exponentially with age. Yeah. Yeah.
Is there a difference in in those graphs for men and women?
Yeah.
Yeah, there are.
Yes, there is difference. And so some diseases women have much more, like autoimmune diseases, lupus 9-1, thyroiditis 9-1, autoimmune diseases, which usually peak around age 50. There's the menopause period, it happens around age 50. And before that, women are protected from heart disease. After that, they get a lot of heart disease. And also bone loss happens around menopause for women, but not for men. And the reason is that estrogen, which is the main sex hormone in women, is protective of blood vessels and bone loss. And men have more cancer. It's probably proportional to size, 10% more. But the kinds of cancers that kill you, both in men and women, lung cancer, colon cancer, and then either breast cancer or prostate cancer. Still, women live longer on average. So, yeah.
You mentioned that the survey was over many years. Is there a change over time because of differences in lifestyle or in medical care?
So what you're asking, the survey was over many years. So there's a problem always with epidemiology, because if you take a group of 90-year-olds and compare them to a group of 20-year-olds, the 20-year-olds grew up with iPhones and the 90-year-olds didn't, etc. So that's always a caveat. And these graphs have not been discovered by us in Clalit. They're like known for about 100 years. So in many different countries, many different cohorts, so these properties of exponential rise and then decline in very old ages is probably not due to a cohort effect. Because they were done 50 years ago, let's say 90 years old, 50 years ago, 90-year-olds today. Of course, you can say maybe this declines because people don't diagnose the disease, but this happens for 1,000 different diseases, so it can't be something specific to a disease. See what I'm saying? So that should be a deeper explanation, as far as I can tell. That's one of the things. That's what I love when you see some patterns like that. What is the explanation? So now is a good time for a break. What time is it? By the way, I don't have my iPhone today. Okay, so we want to explain. Yeah, there were some interesting questions in the break. How can we? Let's say we fit these parameters to data on senescent cells. Can we actually measure things like the speed of the trucks and verify? So yes, Omer Karin in his paper where he fit this to the model also did an experiment to measure the speed of the trucks. The way he did it was give a drug called bleomycin that adds senescent cells, and then look at different time points to see how the senescent cells go back to normal, and that's the speed of the trucks. And he got what the model predicted from here: 5 days half-life at young and 1 month half-life at old, because the trucks get slower. You can also measure the houses. It's not been done by giving, let's say, a senolytic drug, clearing senescent cells, and then seeing how quickly they recover. That's not been done. But what you should see there is that humans are 60 times slower than mice in building houses. What we do know is that humans have much better double-stranded DNA repair than mice. Whales have better than humans. Humans have better than dogs. Dogs have better than mice, etc. And all these epigenetic changes scale with lifespan. Mutation rate scales with lifespan. And so there are, either it's been measured or there are ways to measure. So we have, I would say it's something like trucks. So this is, have rates of days. Houses this is it, let's say human and mouse. By the way, Naveh, who's sitting over there, his master project is to calculate this for lots of different organisms. So this is like, take days, let's say. Houses here, you can say they're built over a century, and here over 2 years. You can say it like that. Noise is like the trucks, time scale. And X critical divided by K. K is like the halfway point of the trucks, which is like the damage you have when you're young, is something like, death happens when your damage is like about 20 times more than the damage you have when you're young. That's what you get in these models. Did I explain myself? So that's, of course, it makes sense that the immune cells in human and mice work in a similar time scale. But because of the repair here, much, much better in humans, and the rate of epigenetic changes much slower in humans, the houses are much, much slower. And we think that's the main knob that tunes the lifespan between mammals. Explain myself? Okay, now let's ask about diseases. What's going on? How come all these different diseases right at such similar times, not identical? Why do they peak? Why do they peak? Why do they peak at different times? But why do they peak at all? It has to be a pan-disease explanation, not specific to diabetes or cancer. So here's what we're going to do. We're going to give you the general principles and then demonstrate it on cancer, and if we have time also on osteoarthritis. Ouch, ouch. So our explanation will be as follows. I'll show you that diseases of old age happen at a threshold. So this person gets this disease here, here, and here, different times. I'll show you how the things that X does to the body, inflammation and stem cell exhaustion, push on the body's physiological systems, move their parameter until something catastrophic happens to the system. I'll show you in cancer, for example. That happens, when that happens, the system changes behavior and you go into disease. I'll be very concrete when I explain it. But that's a threshold cause. So there's an X value, something happens. That is just like the same calculation. You have H0 and you have a slope, exactly the same calculation, except the slope depends on the disease threshold. And the incidence depends on the disease threshold. Okay. Let's take a nice deep sigh of relief. So, okay, if that was all diseases, each disease, we see its slope. We can get. Yeah, let's turn off the. Can you turn off the put it on vibrate. Where's the shelter here? Somebody's pointing over there. I see an iron door. This class will be a lot of getting up, moving. But if this was all, so basically the calculation we did last time is helping us again, explaining the exponential rise. But why does it go down? I mean, death doesn't go down. The risk of dying doesn't go down at a certain age. Risk of disease does. By the way, it's not because people are dying. You take 100 people, 1,000 people that are alive at HT, right? Not people who've died already. So why does it go down? So we need to add another parameter to our model. That this low disease threshold, it's lower than 17, right? Only in what's called susceptible people And the fraction of susceptible people, we'll call it phi, some number between 0 and 1. It's like saying, if you lived a long time, what are the chances of getting the disease? Some people will, some people will never get it. So why does it go down? Because after a certain age, everybody who's susceptible has already gotten it. So when you choose 100,000 people who haven't gotten it at age 90, what can you say about them? Are they susceptible? Most of them are not susceptible. Your cohort is changing. See, at age 80, there's more susceptible people. Some of them get it, but you take them out of the. So this is because. So let's summarize this. They rise exponentially with age because of threshold crossing, and decline because all those susceptible have gotten it already. Right? So we need, for each disease, we have two parameters, threshold and susceptibility. Some diseases are quite rare. IPF, which is a horrible disease where your lung, for unknown reasons, starts turning into scar. You die after a few years. Only lung, it's basically nothing. That's 10 to the minus 4, thank goodness. Things like colon cancer, a few percent. Things like osteoarthritis, a few tens of percent. Things like cataract, 100%. I think everybody will get it. Hearing loss, everyone will get. So very different PHIs, susceptibilities. And we can fit them from this incidence curve, right? The slope gives you XD, and basically the height of the curve, or the integral, gives you phi. Now this fit is amazing because of those 1,000 diseases. The R squared is above 0.9 for more than 90% of the diseases. So it's really good fit. And it captures something quite incredible, which is that the higher the slope, the higher the slope, the later the peak. And the lower the extrapolated incidence. So let me explain that. If I had two diseases and one has a higher slope, you might expect it will peak earlier. But that's not the case. In the data, higher slope peaks later because it starts lower. That's the real, so I'm going to exaggerate here. Higher slope peaks later. So this is information here. The higher the slope, the lower the incidence and the later the peak. That's in the data. Again, it's like, it didn't have to be that way, but that model I told you, with one XD and one phi, but everyone has the same senescence parameters, let's assume, has this property because the intercept drops with XD and the slope grows with XD. I'm just replacing XD for XC because it doesn't matter for the solution what's the threshold. So that's incredible for like 1,000 different curves, this correlation. Or in other words, say the higher the threshold, if you're age 0 now, you ask what's the chance to get osteoarthritis. Of course, it's ridiculous. You don't get it at age 0. It's more an extrapolation. The higher the threshold, noise has to do so much more. It's like the higher the threshold, that initial value is very low. But the slope is higher because of this threshold crossing calculation. Anyway, that's in the world of modeling quite impressive that you can do that. But it's not all diseases that fit so well. There are some exceptions. Exceptions are very interesting. One of them you already asked about is men and women. So some diseases in women don't fit this model so well because This is age 50. This is, for example, loss of bone, osteoporosis in women. It has this extra change here that's not captured by this model. So something about the threshold changes with menopause, probably. So there's some diseases like that. Another interesting set of diseases that's not captured by this model is Alzheimer's disease and dementia. What happens with them is that while all these diseases here are 3 to 8% per year, Alzheimer is 20% per year. It starts much lower in the intercept and it's much faster. So it's a disease of old, and it peaks later. It's a disease of the old, typically. I mean, you can get it at age 65 if you have familial genes. 1% gets familial. We'll talk about Alzheimer, but sporadic Alzheimer, which is more than 95%, 80, 85. But then you have a big chance of getting it, actually, unfortunately. So people say once the price for not dying of heart disease, cancer, or diabetes is that you get Alzheimer. But we have Alzheimer. What does this tell us? In order to fit it to the model, you need XD of 20. Why is that a problem?
Data.
Huh?
Maybe you lack data.
No, because you die at 17. So the slope is too fast for this senescent cell model. So the slope goes with the threshold, as I said. But the slope is so fast, you need a threshold of 20. That's more than the death threshold of 17 to fit it. And that's why we think that there's another X specific for the brain. And we'll talk about that in the Alzheimer lecture.
Why doesn't it start earlier? I suppose there are no 20-year-olds with Alzheimer's.
There are people with Down syndrome, but that's a mutation. But let's say the sporadic Alzheimer is very, very, very rare in young ages, and it's very common at old ages. Why? In what sense? Evolution, mechanism.
Mechanism, maybe?
Yeah, so we'll talk about that in the Alzheimer lecture. Okay, but just keep that in mind. It's an interesting thing you can see from the incidence curves.
So even if you live for longer, if you solve the death threshold, for example, some people won't get any disease, like by this model. Even Alzheimer, maybe.
Yeah.
The people that not.
The people who are not susceptible to any disease will not get any disease, and those people are called centenarians. So people who live to 100 and more, there's a fraction of them that are healthy centenarians. And when you look at their genomes, we'll talk about that in the genetics of aging, centenarians means you live to 100 and more. Super centenarians, 110. World record is debated, either 119-year-old woman in Japan or 122-year-old woman in France. It's not clear. Women. The top 10 oldest people are all women. Yes! And they're really healthy, and the reason is that they are enriched with protective genes. So they can smoke, drink. They do. But they're protected. They get dealt a hand of good protective genes. And that's very good because we can learn from those genes how to prevent different diseases. We'll talk about that in the lecture on genetics of aging. Fascinating field. And this reminds me, why are some people susceptible or not? Because unlike death, where dying, the age where you die is not very genetic or environmental, like I told you. Diseases are. So if you have genes that predispose you to cancer, diabetes, so you have phi equals 1. And if you don't, you have phi equals 0. And environment, if you're eating a lot, too much, you might get obesity, which increases your risk of cancer, your risk of heart disease, your risk of diabetes, and your risk of Alzheimer. don't become obese. Yeah.
The susceptibility is hidden in eta.
No, it's separate. This is everyone has the same eta beta.
Or what
least-
about the noise?
Yeah, the noise also. The noise tells you if you're susceptible whether you'll get it here, here, here. But each disease has its own threshold, and you only have this threshold if you're susceptible. Otherwise, you don't even have that threshold. You just don't get it. That's the model. Of course, it's, again, oversimplification, but it tells you a lot. And even about mechanism. Why are things age-related? So if you go to cancer people here in Weizmann, maybe there's 15 cancer labs. They're world-class, by the way. There was a committee now, an external committee evaluating cancer research, and they said, don't send your postdocs abroad. You can't get a better cancer education than here. Can you believe it? But they study cancer on young mice, because in the cancer field, it's still not a question, you can say, for 90% of the people. Why aging is the biggest risk factor for cancer? What I mean, it's your chances of getting cancer at age 70 are 4,000% more than at age 20. Smoking, it's factor 2. So it's a huge risk factor, aging. It's the risk factor. For most cancers, there's some cancers, young, bones, neurons, etc., but they stop dividing, no more cancer. So that's a big question, right? Why is aging such a big risk factor for cancer? I'm just choosing cancer as an example now, where my goal is to show you that cancer is actually a threshold crossing disease, right? Why do we get cancer? I'm choosing cancer now as an example, but you can do this for many different diseases. So we get into the world of cancer. Wait. Cancer threshold. So cancer, there's, let's say, 100 different kinds of cancer, roughly. 90% of them look like this. Some of them are for young people, but those for old people, they look like this. They go up exponentially, go down. There was an old theory of why that happens that's incorrect, and that's called the multiple hit theory. So in order to get cancer, so what's cancer? Cancer is cells. Normally cells, when they're around other cells, they don't divide. Cancer cells have mutations in their DNA that make them divide even when they're not supposed to. And they start growing. In things like colon cancer, you need a series of mutations. Mutation 1, then mutation 2, then mutation 3, and then you get cancer. And by the way, it's local cancer. What usually kills you is when the cancer goes to another tissue, like colon cancer goes to the brain. It's very, very hard to cure then, even though there's huge advances now by unleashing the immune system to kill the cancer in different ways. But saving people, like in the past, it was impossible, let's say, to live with metastatic cancer. Now, in certain cancers, there's like 10, 20% it can live 10 years thanks to this immune therapy. A big revolution in the past maybe 10 years. But still far away from satisfactory cure. So there's a lot of advances in cancer. So if you have these, let's say you need 3 mutations, and you have probability per unit time mu for a mutation, then you have mu times T cells with mutation 1, mu times T cells squared, mutation 1 and mutation 2, because you need both of them, mu times T times cubed, 3 mutations. So you think the risk of cancer will go up time cubed. So it rises, but it's not exponential. The actual data is exponential. And even cancers that need 1 mutation, like some leukemias that just need 1 translocation, they also rise exponentially. So it's not the multiple hit. Even though you learned that in biology, that's not right.
But when you have 1 mutation, it might increase the chance to have another one. If it's a mutation in the...
Right. Some mutations are what's called, like P53 mutations, you have more mutations later. That's correct. But these mutations in colon cancer in the beginning are not mutators. They don't increase. But so what is causing the exponential rise? So this is called multiple hit theory, and doesn't match the data. So what's going on? I want to tell you what happens to cancer. So first of all, a shocking finding in the last few years where people were able to sequence single cells, their DNA. You find out that in the skin of middle-aged people, there's 30% of the cells have cancer mutations. 30% of the cells. You look at the colon crypts, 1% of colon crypts have cancer mutations. But they don't become cancer. Why? Because once you have a cancer cell and it's become transformed and starts to divide, there are cells called NK cells and macrophages that kill it very effectively. In order for cancer to survive, it had to somehow reach about 1 million cells. Using so much oxygen, there's hypoxia. It calls in blood vessels and starts rearranging its microenvironment and expresses "don't kill me" signals, and then it's dangerous. But in the beginning, those cells are just eaten up by the immune system or competed by neighbors. So it's a myth that cancer cells divide more quickly. They usually divide more slowly than their neighbor cells, unless something's wrong. So if you put them in a dish with normal cells, the normal cells will outcompete them usually. So this is so what's going on here? So we're going to write cancer cell growth is their division minus their removal. So we're going to write this equation. Cancer cell change is their division. So you have a division rate, let's call it proliferation rate, times C, because all cells come from cells. So the rate of cells is how many cancer cells times how many divide. It's different from this production term that doesn't have X here. And this is removal. How many cancer cells times how much are removed. So because all cells come from cells, we can take C outside the parentheses. And this is a very important equation because it shows that whether proliferation or removal are bigger changes the system hugely, because this is cancer cells as a function of time. If proliferation is bigger than removal, they grow exponentially. Right? Solution here is dc dt equals C times something positive, they grow exponentially. But if the second proliferation is less than removal, they get destroyed exponentially. It's like day and night. It's not like just regular protein production where you have some production minus removal. This always has a steady state, P over R, it's stable. Cells are living on a knife's edge because all cells come from cells. If they divide more than they remove, they're going to grow exponentially. If they die more than they proliferate, they're going to decline exponentially. They're very unstable. And all the tissues in our body have feedback loops to make proliferation exactly equal removal as part of your circuits. But cancer cells don't have those circuits. So you see, this is a threshold issue. So if age changes proliferation and removal, you can have a change. So let's analyze that. So here we're going to say senescent cells, X, and actually their inflammation and their TROC usage, they increase P and reduce R. Why is that? Let's write that. Here's now I'm writing senescent cells in the body. Here's P. So proliferation rate of cancer cells, these are normal cells. When you have more inflammation, as I told you, is an alarm signal, just like we would run to the shelter and we would stop proliferating. Same with the regular cells. So when there's inflammation, cancer cells have advantage. What about removal? Proliferation or division, right? Removal. The trucks that remove senescent cells are also the ones that remove cancer cells. So the more X, the less those trucks. I don't care what the shape is, but it's reducing. Now in most people, the lines never cross. And you see, but if you're susceptible, the lines do cross. They cross at this magic point, which we'll call XD. If you have less senescent cells, removal is more than proliferation, and the cancer cell goes away. Once I'm here, proliferation is more than removal, and the cancer grows. So this is why it's a threshold crossing event. There is a critical level of X where proliferation crosses removal. The susceptibility has to do with many things. If you inherit a mutation, all your cells have a mutation. It's much more likely to get the other two mutations. You have many more cancer cells. Depending on their niche, they have different proliferation removal rates. There'll be one with the highest proliferation rates, and that's the one who's going to cross. So if you're born with that's your genetics. Like I said, if you're obese, you have inflammation already because of obesity. So inflammation increases P relative to the other cells. You have insulin. Insulin is a growth factor for lots of cancers. Why do you have insulin? Because, well, we'll talk about that. You're insulin resistant. So those risk factors can determine if you're susceptible or not. That's to say if those lines cross or not. Did I explain myself? Yeah?
So surgeries that remove tumor mass move me from the right side to the left side for X amount of time?
No. If you remove the tumor mass, you still have your senescent cells high. So if you have one cancer cell left somewhere, it's going to regrow. That's the problem. In brain cancer, for example, you can't avoid it in GBM. It's always going to come back. And so
I need,
if it's exponentially growing, you need. If you take a senolytic, okay. So then maybe just say something about medicine. Right now, we treat each of these diseases when we get them: diabetes, cancer. The idea of the field of neuroscience is that if you treat their underlying risk factor, aging, in one fell swoop, you reduce the incidence of 1,000 diseases. That's called the neuroscience hypothesis. If you slow down aging, you reduce the incidence of all the aging-related diseases, which is needless to say, a revolution in medicine. Great.
Why
Yeah.
don't we have a Michaelis-Menten-like relationship in DCBT? Like the term that we had in DHD, beta x by k plus x. Why don't we have something?
You could add that, but it won't change anything.
Or maybe like unstable state.
Yeah, it's an unstable steady state. It's not actually a steady state because this x is a parameter, comes from the outside, from the senescent cell model, and it rises with age, right? You start with low x. You start with low x, and as you age, x goes and at some point, some age, it crosses, and that's when your cancer starts growing. You get diagnosed a few years later.
Why they don't study state? It's not when this equals 0.
In order to get steady state here, you have P equals R. In order to do that, the only way to do that is with feedback loops. So the liver also has the same equation, but the liver growth rate is determined by the liver function, and that's how we get a feedback loop that logs P and R. But in cancer, it doesn't have that feedback loop. That's the whole point of cancer. It goes up, and if you think, and by the way, okay, if you think that this is just for cancer, then I want to tell you it's for a huge class of diseases. For example, we know that death from infection like COVID rises exponentially with age. You know that? Death from COVID rises exponentially with age? it's really it's the same idea. Here are virus-infected cells. They make more virus-infected cells because the virus leaves and infects more cells. And they're removed by the same trucks. So it's the same equation. And it's, again, the same threshold crossing. It's different for each virus, etc. I mean, some viruses kill young people because of their immune system. It's not all viruses, but a lot of viruses have exponential mortality risk. So it's the same equation. Now, there's a whole other class of diseases where the problem is not cells growing too much or virus growing too much. The problem is cells dying too much. And again, it's the same equation where you have senescence. For instance, in this lung fibrosis disease I told you about, these are not cancer cells now. They're trying to stay P equals R. Yeah? But what inflammation does, stem cells do this stem cell exhaustion thing. So in tissues where you have a lot of removal, like in the lung tissue where cells are removed, the stem cells need to replenish them. But if there's stem cell exhaustion, at some point that replenishment potential goes below the removal. And then you have a collapse. Lung cells die, they have to be replaced by something, by scar. And then the rest of the lung has to work harder. Those cells die, replaced by scar. So that scarring goes from the outside in, and you die. Now, this is only in 10 to the minus 4 of people. What's the susceptibility here? Susceptibility is smoking, plus things like asbestos, plus genes where you have some genetics that just increases the removal rate of those cells, like telomerase mutations, all kinds of mutations. And so in most people, proliferation drops, but never crosses removal. But susceptible people, removal is so high, when you're young, you don't feel it, but bang. So that's susceptibility. And there's a mathematically analogous disease that sounds completely different. That's the knee disease I told you about, osteoarthritis. I didn't, of course, I started lecture, I already knew I'm going to get to it, right? I just didn't mention those. So this painful disease here, what's going on? Your knees, the joints, are this amazing material that can bear your weight and has nature's smoothest surface at the synovial joint, like friction almost zero. And when you're 20, 30, they're fine. When you're 70, suddenly there's a hole in your it goes through the bone. What's going on here? There's cells in that cartilage, it's a biological material, that make those fibers. They're called chondrocytes. And those chondrocytes come from chondrocyte stem cells. And again, they need to be replaced once in a while. So that's no problem. Stem cells divide, replace them. But if there's stem cell exhaustion, and you're overweight, and your feet are like this, so all your weight is here, the removal rate here is so high that at a certain age proliferation goes below it. And then the chondrocyte here die. The other chondrocytes start to make these tough fibers, collagen 1. Collagen 1 is very brittle. The cartilage breaks and you have a hole. So again, it's a threshold crossing thing, except now proliferation goes below removal. Why? Because that's the way SAS pushes the parameters of the system. And you can go disease by disease to understand what parameters get pushed beyond a bifurcation point, a point where things change dramatically, and even understand mechanisms for disease. Like this IPF disease, it's called idiopathic pulmonary fibrosis because idiopathic means we don't know why it happens. But it gives you a mechanism why it happens. And what's the damage? Right? The damage, age-related loss of proliferation capacity exceeds removal. And it's a mathematical generalization, you can say, that unites very different diseases. How quickly disease progress has to do with how quickly the cells divide. So in the cartilage, it's a very slow process. It can take a decade. In the lung, it takes years. But years once you cross the threshold till the disease kills you, you can say, or is manifest. But the idea is the threshold crossing. Okay, we have time for questions.
Is there maybe a way to give an alternative explanation for the fact that this like threshold crossing, it's not with the number of senescent cells, but there's some like intrinsic properties of the NK cells and the macrophages that just like some people don't have the right amount or they're not as effective?
So you're saying another factor that can vary between people is the trucks are less effective. I think if the trucks are less effective in a certain group of people, they'll have a whole suite of problems. They'll have both cancer, diabetes at an early age. And that happens in a disease called progeria, where you get all these diseases like at age 40. And they're usually diseases here, in this repair. But that's definitely another. So this is what's called computing with the truck model.
Could you give condition on the removal part of the equation? I get why the polyflexion is linear with the number of cells, cancer cells and viral cells, but why the removal should be linear with C?
This is okay. Why removal should be? This is like you can say that each cancer cell has a certain lifetime because of the immune system, but you can also add something like this here, right? If you want to, and I invite you to try to solve it. It's still gonna be a problem, even more of a problem. But there are actually this is used now in some experimental cures for cancer. It's called farming the cancer. So if you can't get rid of the cancer, you can at least use the fact that large cancers inhibit their own removal like that, and then they're removed more slowly. So you kind of farm it. You treat it a little bit, you let it grow, treat it. That's an approach. Treat cancer. I mean, there's so many different approaches to kill cancer. You can now engineer T cells, give them artificial receptors that target cancer and inject them back. Your own T cells, play with them, inject them back. And you can block the don't kill me signals. You can, chemotherapy is a poison that kills dividing cells, so it also messes up with your hair and your intestine. Let's say like this. If you need to treat the cancer, that's not so good. If you can prevent the cancer, much better. And in between, there's what's called screening for cancer, which means try to detect it when it's still small, because then it's much easier to treat. So colonoscopy, mammography, and now there's also a revolution in that. The cancer cells, when they die, they release their DNA into the blood, which lives there for a very short time. But sequencing has gotten so good that you can sequence DNA, free DNA in the blood, and detect cancer, and even what kind of cancer it is, based on the methylation patterns and the mutations. That's called liquid biopsy, and it's like working. It's not perfect yet, but it's already commercial. The problem is you get overdiagnosed, so you think you have. It's not. How do you call it? The false positive rate is high. Yeah, but some tumors, like pancreatic tumor, it's so hard to detect that once you detect it, it's already spread to other organs, and you die very quickly from it. It's really the seventh biggest killer. And what's the fifth biggest or fourth biggest killer in the Western world? Medical errors. More questions? Yeah.
I sort of don't understand how the threshold models coexist with the susceptibility.
Okay.
Because if someone is not susceptible to disease, I would guess that there is no threshold point where the production equals the rate. So
right.
It looks like a non-biological.
Okay. Non-susceptible. It looks something like this. Removal, proliferation.
But then at some point it crosses.
Crosses, but let's say if this is the death threshold, crosses when you're age 200.
So it's not like they are not susceptible. It's just that you cannot see their susceptibility.
I agree. I would say that non-susceptible people have XD here. I agree. I think, again, it's one of those things where eventually you probably get a lot of different cancers. Actually, a lot of people, in autopsy, you find cancers that are just not in different stages. More than more than 30% get a cancer, skin cancer called basal cell carcinoma. Old people, you see this kind of greenish bumps under skin or something. So almost everyone gets it, but it's not. It doesn't make metastasis very often. So that it's like, I guess if you're old enough, what you're saying is everyone is susceptible if you don't die.
But then doesn't it like changes what we talked about calculating this susceptibility?
Yeah,
index, and then
you're right. Why do things go down?
Yeah.
So I guess what I said is wrong.
Yeah, this is what I don't understand.
Yeah.
How,
Yeah, I guess I don't understand it either, but maybe they'll never get it.
Maybe,
See, that's great about teaching. You can see that you don't understand your own material.
maybe like you have to have something in order for this to be like significantly more like lower, and then there are people who have like it doesn't like you won't see it if it will be like 10 times higher than that threshold.
Oh yeah, right. So
you
like
wouldn't see it.
susceptible means it's either here or here, and then everyone who's crossed it already and didn't get it won't get it. So it could be like that. So that it's like bimodal. Either the threshold is 30 or. By the way, the sudden diseases, their thresholds are between 12 and 16 generally. The fits.
So everybody dies from something, right?
Yeah.
Day, right? So what does it really mean to have like different threshold for death, which is not associated?
Okay.
with disease?
So the question is everyone dies from something, but I think it's a mistake to think that everybody dies from a disease, because there's also death of old age. Or you can say, for instance, a lot of times you break your hip, go into the hospital, you die of pneumonia. You actually died from the hip break, but you actually died because you don't have enough muscle mass and stability, and you don't have enough money to pay for light, so you turn off your electricity. You have to pee in the middle of the night because your bladder is old. You forgot that you put a new rug there. You start slipping, but you don't have enough muscle mass and stability to stop yourself. You see, it's like a compound thing. What did you die of? Social economic status, loss of muscle mass, loss of stability, loss of vision, maybe you didn't see, immune compromise.
So it's basically just like an all-in-all decline that brought you somewhere.
Yeah, so you can't write in the coroner's report reason for dying old age. You have to write something, but in the end, a lot of it is old age. And not everybody. I mean, a lot of people die with these diseases. Some diseases are really deadly, like pancreatic cancer. You die less than a year. GBM, glioblastoma, less than a year. But a lot of them are chronic, so it's really a human being is so complex. So this risk of death is like, I guess it's a compound of many effects. Let's say all driven by 1 or 2 or 3 X's like that, we think.
Is the equivalent to some X there, or is it something else?
I don't know. That's a great question. I don't know. I think it's something else. Also, the way we see death is much more clear than if we see cancer rates. The data is better. I mean, the susceptibility is 1. It's different. I think it's different. Yeah. What do you think, Glenn? Is death different from disease? Like, is this threshold specifically different?
It's gotta be somewhat
Fundamentally different, right? I think so too. So, by the way, Glenn is a postdoc studying longitudinal health data and getting a lot of insights about diseases and decline from longitudinal human health data. Okay, let's take a nice deep sigh of relief. Thank you for asking all these great questions and being with me on the journey. And see you next week.